This is example 5.5 from Discovering Design with Chemistry. And this problem asks, is SF2 polar or nonpolar? So this was one of the comprehension check problems, number 12, so you should already know the shape, but just in case you didn't, we'll go ahead and fill this out real quick. So S is in the 6th column, so it has 6 around it. 1, 2, 3, 4, 5, 6. And then F is in the 7th column, so it's going to have 7 around it. 1, 2, 3, 4, 5, 6, 7. And then same for this one. 1, 2, 3, 4, 5, 6, 7. Notice that I strategically laid these out already so that you could see that these two pair up. I should have used different colors to make this easier to see. And these two pair up. So we end up with a single bond on both of those sides, but the S also has these other two. So S has stuff, and we could have put the F down here or over here. It doesn't really matter. The important thing is that this S has 1, 2, 3, 4 electrons either as a pair or as a bond on all 4 sides, which means it's going to be sort of like the way the tetrahedral was, but with only 2 sticks. And so it ends up being a bent shape. So that we already know. So the thing we have to figure out if it's polar or nonpolar is there a pull in more than, is there just a direction of one direction where things are being pulled, or like multiple directions to kind of make it unbalanced? So in the book, there is a nice little chart that helps you as you're getting used to this electronegativity stuff. And if you notice, S is here and F is here. And you should be able to do this with just a regular periodic table using being able to find these two. In this case, you can see that F is both to the right and up from S. And so we know that electronegativity increases as it goes in this direction. And so for this one, F is more electronegative than S, and so the electrons are going to be pulled to the F's. And so we're going to change these to arrows that are pointing to the F's. So now you can see that the electrons are being pulled diagonally downwards, and they're both being pulled in opposite directions, but there's nothing pulling it back up. And so even though these are kind of going in sort of opposite directions, they're both just going down, and so there is a pull, and so this one would be polar because of that. All right. In the book, I think the Lewis structure was down here, and so that makes it a little easier to see. But either one, you can still see that once you get the shape drawn correctly, and once you check out your electronegativity chart or have it kind of memorized so that you can do it from there, you can see where it's going. All right, so let's look at this one. We haven't done the shape of this molecule in any of the examples, so first we're going to start with the Lewis structure. There are 2, and we're going to do this without our dots. There are 2 oxygen and 1 silicon. So let's start with the silicon. It's in column 4, so we have 1, 2, 3, 4. I don't think oxygen's going to beat that. This one's going to be in the middle. So let's put our oxygen one. Let's put 1 here, and let's put 1 here. Now oxygen is in column 6, so it's going to have 6 around it. I'm going to go ahead and put 1 of the 6 right here. 1, 2, 3, 4, 5, 6. And same thing over here. I'm going to go ahead and put 1 of, you know what, let me erase this and use a different color for oxygen, because that'll make it easier to see what's going on. So there's my silicon with the 4. Let's make oxygen be red. And let's give it 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so now we have to move the other 2 dots on the silicon that aren't paired yet. And so to do that, we're gonna have to move things around to make that happen. So let's go ahead and move this one, this red one, into there. And let's move this blue one also into there. And then we can get rid of them. Oh, my marker is unhappy about erasing. Okay. And then the same thing is going to happen with these other 2. So this one, we're going to put it here. And this one, we're going to put here. So we now have a double bond here and a double bond here. So in this case, silicon only has two like movable electron things. It doesn't have any floating up here. It doesn't have any bonds up here. It just has a double bond here and a double bond here. And because it only has two things, and it might be easier to see if I had made them in a line, but because it only has two, it's linear. In fact, I'll move it over here so you can kind of see what's going on there. So let's take these double bonds and let's shift them over here. And then we'll move the other two. Wow, my markers are horrible. This is oxygen. All right, so hopefully that's a little bit easier to see that it's linear. Yep, I'm going to be cleaning my board with chemical after this video. All right, so anyways, so it's linear as it is, and so we probably could just see from there, but just in case you can't, we need to look and see where are these in the periodic table. Oxygen is up from, where is, look, oh, there it is. It's up from there, and it's to the right of here. So we have to go right and up. So this one's going to be more electronegative. And so the oxygen is going to be where the electrons are being pulled. And so if we rewrote this as Si, and we put our double bonds here and here, put our oxygens here and here, and we left our little dots, we would need to add arrows to this. I'm just going to add like a giant arrow colored in, kind of like they did in the book. Because the oxygen is more electronegative, it pulls on those electrons, and so it looks like this. In this case, there's pulling happening, but it's in the opposite direction, like exactly opposite direction. So this one's being pulled this way, this one's being pulled that way, kind of like two kids with a tug of rope. They're equally matched kids. They're both pulling in opposite directions. So this one's not going to be pulled unevenly. So this one is nonpolar. All right. And then we have one more, but I'm going to have to erase the board, so hold on. Okay, our last one in this example asks if SiF2Cl2 is polar or nonpolar. So let's start with what we know. So Si is in column 4, so I'm going to assume based on that, make these fatter so they don't look like the I dot, that this is probably going to be the one with the most unpaired electrons since it has one on every side. So then we have two F's and two Cl's to deal with. Those are both in column 7. So they're both going to have one unpaired electron. So we can kind of put this anywhere we want. So we're going to put the Cl's on the sides and the F's on the top and the bottom. So because, let me pick a different color. So F has 7. So 1, 2, 3, 4, 5, 6, 7. And that's perfect. And we're done. 1, 2, 3, 4, 5, 6, 7, and we're done. And then the Cl's 1, 2, 3, 4, 5, 6, 7. I know I'm supposed to put them on one side at a time first and then go back and fill in, but I could see what was going to happen. So to redraw this Lewis structure, so it has the bonds drawn in. We would have Si, Cl, Cl, F, F, and then we could add all of our dots in. And I'm just going to add them all in black marker for simplicity. Curious to see if my board likes the pen and gear markers better than the shuttle art markers they kept smearing. We will see. Okay, so now let's look at our periodic table and let's find those elements over here. And we want to see if we can do this without the electronegativity chart that's in the book. In my book, it's on page 138, but the text wants you to be able to use a periodic table that's not colored with electronegativity coloring to be able to determine this. So Si is here, and then here's your Cl and here's your F. Both of these are to the right or to the right and up. So these two are going to be more electronegative than the Si. So we're definitely going to draw our arrows going away from these. Let's redraw this with the correct shape so that we have the shape. This has 4 things happening around it, so it's going to be tetrahedral. So think about the Si is going to be like a stool with a with a stick out the top. So we're going to put one leg on the plane, one leg sticking out from our paper. I'm going to make it kind of fat and then put the thing on there. And then the other is going to kind of be going into the back of our paper. I am not very good at the dash line ones. Oh yeah, that does erase so much better. The book kind of draws them like little sideways lines. All right, that is supposed to be a tetrahedral shape, and they're all pulling in opposite directions. But the question is, are they all pulling equally in opposite directions? Because for it to be nonpolar and have that kind of balance where nothing's pulling too strong in one direction or the other, they all have to be equal. Well, when we looked at the F and the CL, which are right here, the F is higher. It's up more on the chart from the CL. And remember, as we go to the right and up, we become more electronegative. And so in this case, fluorine being above chlorine on the periodic table means that fluorine is more electronegative. And so these Fs are going to be pulling a little bit harder. I don't really know how to indicate that on this. I'll make the arrows a little bit bigger. And so they're not being pulled equally in all directions, even though it's being pulled in all directions. The fluorine's pulling a little bit harder. And so that means this one is going to be polar because it has not equal pull in all directions. And it kind of looks like the chlorines cancel each other out because they're kind of across from each other. And it kind of looks like these cancel out, but you have to think of this like in a 3D shape. Because if it were in a 3D shape, like imagine like a little three-legged stool with a stick coming up out of the top of it. If the stick coming out of the top and one of the legs going down were pulling harder than the other two legs, that it would make it unbalanced, if that makes sense. Anyways, this one's polar.